Hello and welcome to this next lecture on foundations of machine learning. Today we will conclude our discussion on convolutional neural networks and then go on to recurrent neural networks, which is another very interesting class. So recall the convolutional filter which we are now illustrating on images. So given an input image 200 by 200 with 3 attributes per pixel corresponding to R, G and B, and given a convolutional filter which is of size 5 by 5 by 3, the idea is basically to slide this patch across the length and breadth of the image. Now how much can you slide? Well, you certainly need to ensure that there is at least one pixel overlap between the patch and image at all points of time. So need to ensure that there is at least one pixel overlap between the patch and image at all points of time. So what does this mean? Well, this means that if the patch were to begin at, say, this position with one column overlap, and suppose you were to move it all the way to the right, then how much would you move? You'll certainly need to first cover the 4 pixels and then ensuring that this leftmost cell in its final state is the only one that overlaps with the image. This is how far you can go. So how much would you move? 4 initially and then 200. So this should give you an idea what the size of the output layer should be. You like 200 plus 4, 204, and likewise with the number of columns you would like 204. So this is how the output layer or the hidden layer corresponding to the input layer would look like. For the sake of convenience, we will refer to this as the input layer and this as the first hidden layer. However, going forward, this input could correspond to the L minus 1th layer and the output in general could correspond to the Lth layer. So if you had a stride length of 1, you would move 204 steps to the right and 204 steps below. Here we see the filter shifted to the right by stride of 1 and so on. As already suggested, you'll have the similar number of moves to the bottom. So here's a summary. Given an input image of size 200 by 200 by 3, a very primitive or naive implementation using multi-layer perceptrons would lead to 4.8 billion parameters. Do you do better with the CNN? Well, we already saw that with 20 feature maps, each of size 5 by 5 by 3, you would basically need the number of parameters to be 20 into 5 into 5 into 3, which is 1500, which is way below the complexity, the number of parameters in an MLP. How about neurons? So given the input image of size m by n by 3, and if p by q by 3 happens to be the dimension of the patch, in our specific case m was 200, n was 200, p and q were 5 respectively. If s were the stride length, the output size would be m plus p. This is how much I can move to the right divided by s, but I need to subtract this 1 because I would like to discard the corner cases when the kernel has no overlap with the image. This is along the length. Similarly, along the breadth, you will have n plus q divided by s, and you subtract a 1 to discard the corner case. So in the specific example, we would have 20 into 200 plus 5 divided by stride minus 1 into 200 plus 5 divided by stride minus 1, which amounts to around 832,000 or 830,000, which can actually increase with max pooling. So interestingly, we have increased the number of neurons in the hidden layer from the earlier value of 40k to around 830,000. So there is a trade-off. Note that the number of parameters which were earlier 4.8 billion have now reduced to just 1500. Number of hidden neurons have however gone up from 40,000 all the way to 832,320. So we have made the model more complex in terms of structure, but simplified in terms of parameters. This is primarily because of parameter sharing. So we can manage to train more effectively with the data we have. We'll have to do a lot more computations. So that is the price we pay for more complex structure. Well, it is apparently more computation, but note that even with the previous model with 4.8 billion weights, you anyways had to do a lot of weight multiplication with the activation or the input from the previous layer. We have, in that sense, fewer weights to multiply, but we have more nodes where these weights will reflect. So CNNs have been very effective in classification, object recognition, etc. with images. So recall the Lego blocks in modern deep learning. We have so far discussed feature maps. All that we have discussed so far was a single feature map. You just multiply this with the number of feature maps. Discuss kernels, strides and padding. We will now discuss some additional filters. So recall that kernel was a kind of filter which took input from several pixels and generated a single output. You can similarly take multiple inputs and generate a single output through pooling or max pooling, which also results in downsampling. So strides did give you some downsampling, pooling gives you downsampling of a different kind. It's of course also a filter. We'll then move on to discuss RNNs and LSTMs. So far our motivating example has been images. For RNN, recurrent neural networks, and long short-term memory networks, we'll have the canonical example of text. So let's say you want to build language models, you want to predict the next character, you want to perform some machine translation, you're dealing with sequences, and especially sequences where the prediction of the next character or the next word depends on what has already been seen so far and what has been already predicted in the model so far. But let's first do pooling. So the max pooling filter is a very special purpose filter that selects the maximum value from the patch. You can understand it to be sample based discretization process where the sampling is based on the max value. You could also look at other criteria for sampling. This can be especially useful if you have an internal representation of the object and you want to allow for translation invariance. Now what does this translation invariance mean? It's possible that you have an image with a cat somewhere here or a human being somewhere here, and let's say you had another image where the human being moved perhaps slightly to the right or the left. Now if you have an existing internal representation of the image, the invariance would be with respect to translation across the image without any restrictions on how much the translation is. If you are operating of course directly on the input layer, you might capture the translation only marginally. So even as you move this human being, what you are interested in is features such as head being above the body. Max pooling just says, well, I don't care for the exact location as long as I can ensure that the head is above the body. This also helps you achieve dimensionality reduction by downsampling. So number of parameters that are required to learn gets drastically reduced, and in this process you also help avoid overfitting. So operationally what this will mean is that for the patch in the image on which you are operating this filter, you will only pick the max value. Now what should be the size of the output when you apply a specific max pooling filter? Let's understand this through a simple example in the one-dimensional case. So our discussion continues to remain about single feature maps, and all that we are talking about extends to multiple feature maps simply by multiplying with the number of feature maps. So let's say the input was 4, 5, 6, 7, 8 and you have a max pooling filter of size 3. The output from the first section is 6. Note that max pooling filter simply cannot operate in empty space. So what you cannot have is this filter moving further to the left. As you can see, this should already help you get much smaller output layer than the output layer that resulted from a standard convolutional filter. As we move this to the right by a stride of 1, we find 7, and with one more movement we get 8. Now again you can't let the filter move any more to the right. So the size of the output happens to be 3 when the size of the filter is 3 and the input size is 5. So if the input size were m, you would immediately subtract the size of the filter p and of course divide by the size s. However, you will need to adjust for 1 because you have subtracted one cell too much in m minus p. So this is m minus p by s plus 1. This will be the size of the output layer. In this specific case, m was 5, p was 3, s was 1, and you can verify that this turns out to be 3 as we saw. What will be the output if input and max pooling filter remain the same but stride changes to 2? First of all, we estimate m minus p by s plus 1, which is 5 minus 3 by 2 plus 1, which is just 2. So we expect the output size to be 2, and we can verify in this process that the second shift would never take place. You would actually jump to the third right away. So the output we expect is just 6 and then 8. Right, 6 and 8. Now in general, if you do max pooling in 2D for a single feature map, m by n by 3 is the dimension of image, p by q by 3 is the dimension of patch. So the output size would now generalize from m minus p by s plus 1 to m minus p by s plus 1 cross n minus q by s plus 1. Right, if you have, for example, a 3D image with m equals n equals 5, p equals q equals 3, the output size will be 3 by 3 by 1. This is with the